Hey, John here. Let's talk about references. References are, in the simplest of terms, an alias for another variable. Let's look at this code down here in main. I have a variable called num, and I've given it the value 5. Right here I have an int ampersand, and I have this rnum variable here, right? Now remember, when you declare something that's a pointer, you do it like this. Let's say I say star p, right, might equal, then I would have to say ampersand num. So I would then say p, as a comment, is a pointer to num. Oops. Now, what's the difference between this pointer to num and this reference to num, this alias of num, all right? Well, on the one hand, the pointer, as you know, is a variable in its own right. I can assign p a new value. I can point it somewhere else. A reference is a one-and-done kind of a thing. It says rnum is a reference to num. You must initialize rnum. When you define rnum, you can never change rnum to refer to any other integer. If I want to, I can do this and change p later on, okay? This is okay down here. It would not be okay to change rnum to refer to some other variable. We could try, and the compiler would complain. Let me delete this to eliminate the confusion. So anyway, the point is here that you have an ampersand in front of the variable when you define it versus the asterisk, okay? And again, the rule of changing it afterwards is real. One of the main differences here. All right. So what is this all about? Let's look at some code here. I'm going to print out the value of num. I'm going to print out the address of num. All right. This is going to be. This is, now I'm grabbing the address. Just putting an ampersand down here, remember, means the address of the variable that follows this thing over here. Okay. When you put the ampersand in here, you're saying, I'm declaring rnum to be a reference to an integer or an alias of an integer, okay? Don't confuse the ampersand here with ampersands anywhere else in the code, okay? I can then come down here and I can print out the value of rnum, and I can print the address of rnum, okay? I can pass num to a subroutine. We'll look at this in a minute. We can pass rnum to a subroutine. We could print out number and r number after the subroutine call. We could print it out, after the second subroutine call. Let's look at what happens in this subroutine. Up here, I have a parameter to the subroutine that's a reference, right? Again, remember the ampersand in a definition says numref is a reference to an integer. If I put an asterisk in there, it would be a pointer to an integer. What's the difference? Well, in a lot of ways, there's not much, okay? Down inside here, I can print out the value of numref. I don't have to put the asterisk in front of it. Why? Because it's not a pointer, it's a reference. It is an alias of this variable down here. And the point of this is that that can extend through into a subroutine. So if I assign a new value to numref like I do down here, what I'm really doing is modifying the number variable down there. If this was a pointer, I would say star numref plus equals 10 and accomplish the same thing. If I wanted to print the value of a pointer, the variable that a pointer referred to, I'd have to put a star in front of this. If I wanted to print the address that the pointer has, I would remove the ampersand here, right? We already went through this when we were talking about pointers. All right, so we print out information about this numref variable at the beginning of the subroutine. We add 10. We print out its value when we're done. And we go back to main down here. Main turns around, and notice it passes num the first time and rnum the second time. And since rnum is a reference to num, it's really passing the same thing, okay? And since numref is a reference to whatever variable is passed, okay, a reference to a reference to a reference is still another alias of num. Okay, so let's go ahead and compile this and run this. Oops. and see what happened here. So what do? We got main. It prints out num. Num is 5. The address of num is that thing, right? It's on the call stack and the activation record for main. It's a local variable inside main. Main also then prints out the value of rnum. Remember, we never assigned rnum a value. We said, well, I mean, you could argue we assigned it a value, but what we really did here is assigned it the reference. And this will be driven home by the next bit of output. Rnum is the value 5. Its address is the same address as num. So to the compiler, this name really is the same thing as that name. There's no difference. They're both variables that represent the value of an integer who's stored somewhere in the memory, and that value is stored at the exact same address. So these are, for all intents and purposes, the same thing. We then, as you recall, passed num into this subroutine here, and it prints out its value 5. It says, oh, what's the address of that thing? Notice this address is the same as all these. So that alias reached into this subroutine here. We added 10 to it. We printed it out inside the subroutine. So now it equals 15. We returned to main, and we printed out the value after we came back into main. We had printed both num and rnum out, and we see they both modified. Why? Because the subroutine modified the value of an integer at that address, which is the same as all these other things, okay? They're all just different names for the same thing. We then come to the end of main, as you recall. Down here, I pass rnum into this subroutine the second time, and again, I print out the same results as we did before. So when we go into the subroutine the second time, numRef refers to an integer whose value is currently 15, because it was adjusted by the last call. The address of numRef is this number here, and notice I ran it again, and the stack changed. Therefore, all these are still the same. They refer to the same address and the same variable, but it's a different address than the last time I ran it up here, so don't get thrown off because of this, all right? Each time you run it, everything could be in memory in a different location. That's a given, all right? Never bank on that being the same. Anyway, so what happens the second time we go and add int? Same thing happened the first time. It prints it out. We say, here's the address where that thing is stored. I'm going to add 10 to it and print it out. It's now 25. Return to main, and main's going to print out the values of its local variables after it comes back from add to int, okay? So what does all this mean? Add to int with a reference definition right here. Let's look very closely so we all understand exactly what's happening here. This can be very subtle. And this is gratuitous, by the way. No one in their right mind would just simply define an alias right here as a local variable for no good reason. I mean, this is just foolishness, okay? But declaring them as function parameters is what you're going to see happening a lot. Okay, so this is what we got to get used to this. While this is true and legal and can make sense, like I said, it's kind of pointless and can cause all kinds of disorientation to a programmer thinking rnum and num are different, because normally they would be. You would just normally not do this, all right? But my point of bringing all this up is that when I call this add to int function, and this guy defines numRef as an integer, or as a reference to this integer up here, look what happened the first time I called it. I said add to int, and I sent it num, and num is an integer. It looks like I passed num by value. I find personally this to be an incredibly annoying feature of references. You cannot know by looking at this code in C++ whether num was in fact passed by value or whether it was passed by reference until you go and look at the definition of this function up here. Because this function defines numRef as a reference, this function is stealing, in a way, in my mind, this function here steals the reference to this passed-in variable down here. So if you naively, wander through your program and you're writing this code and you call this subroutine and you pass num, and if you're a C programmer, because C does not have references, there would be no way for this function to modify the value of this num variable simply because you did not pass it the address of num. But in C++, because we can kind of steal this reference to this argument, this function can modify it because of this. All right? I find that a little annoying. You just need to be aware of more things than you would otherwise if we didn't have these references. Down here, notice I'm passing rnum, which is defined to be a reference to num. Both of these work. There's no difference in the behavior of num, which is an int, and the behavior of rnum, which is a reference to an int. Once it has been defined and initialized like this, rnum and num are simply just integers from the grammatical construct that is this code up here, all right? This guy up here can steal the reference to the argument, whether the argument is passed as an int or as an int reference. Okay, that's the whole point of this little diversion here. Okay, this guy thieves this thing off of the caller and he can modify it. Now let's look at some issues here. Okay, obviously this can be confusing. So what normally happens, if you want to define a function that needs the value of an argument over here, and you want to grab it by reference, you can declare it as const. And you're then guaranteeing to the caller down here that you will not modify the value of the variable that you grabbed by reference. In this particular case, it would have been easier just to pass the int down there. Okay? However, if the data type of this variable is more complicated and consumes a large amount of memory, you don't necessarily want to make copies unless you need to. So if you grab a reference to something and declare it as const, you're writing more efficient code. All right, so that's one way to do this. Otherwise, you can use a pointer or a pointer to a const, and we talked about that before as well. So this all kind of goes along hand in hand. Now, remember, this function does try to modify numref. So in this particular case, declaring it as a const is a problem. And if we compile this, the compiler will say you can't do that because you're assigning a read-only reference as opposed to a modifiable one, all right? So if you do a const and try to refer to and modify the thing that's been defined as const, you'll get that compiler error. So that helps you debug your code, okay? Now, if you have a function that does not modify it, go ahead and make it const. In fact, you want to use const liberally on all references unless you need to modify them, all right? You'll see that thematically through all the standard libraries and stuff like that in C++ programs. All right, so add to int can also return, if we want to, a reference. I mean, references, pointers, values, no matter what you can define in C and C++, if it's legal to define, it's legal to use anywhere any other variable can go. All right? If I want to, I could do this, and I could return, for example, I could return numref like this. And what would happen is it would return back to the caller a reference to numref. And you see this happen in C++ apps all the time. Now, this usually deals with operator overloading and more advanced features. So right now, this is just very gratuitous. Why would the caller need to be told where his own variable is? All right. Trust me, there are times when this is very handy for you to have. So let's go ahead and compile this to make sure that I didn't lie to you. All right, it compiles, everybody's happy. If we want to, if I do this, here's how you would use such a thing. Well, look at this. Yikes, right? What the heck does that do? Well, this is going to go to add to int, and it's going to add 10 to the variable that's referred to by this variable name, okay? And when it's done, it's going to return a reference back to this same variable, which is then going to be incremented by 1. And then I'm going to print this out again down here, right? So we know that we were up to, what, 25 down here? Because it starts out as 5. We call this, it adds 10. So it prints out a 15. We call it again. With the reference, it goes to 25. Let's call it again. And it'll now go to 36, right? And it really doesn't matter whether I pass it num here or rnum. So let's eliminate the confusion there, all right? So this guy steals a reference to num, does his adding, and then we return and we add 1 to it. Okay, so now things are getting a little bit more tricky. Now this is gratuitous, all right? You want to write code that does this, you're just being a jerk, okay? Don't do that. There are times where this is incredibly valuable and incredibly useful, and we will see it as time goes on. Don't just start going willy-nilly with this stuff crazy, all right? Just wanted to see you to see this, because I want you to understand that this concept of aliasing can reach through and permeate all over the place in C++. All right, it's returning a reference up here, and because the reference is the same as a variable in almost every way, this represents num because how it was returned. All right. Now let's talk about a little bit of terminology here. Well, C++ came along after C. And in fact, the original concept of C++ did not include references. They were only added to deal with a grammatical construct that could cause confusion and ambiguity that has to do with what we call operator overloading. The point is, references are pretty straightforward and simple, but they were invented to solve a rather complicated problem. We'll encounter that problem later on. Meanwhile, we need to understand what a reference is and how it works so that we can use standard library routines that declare their parameters like we did up here. There are a lot of standard library calls that take references. Now you know what they are and you know how they work. And you can either have a const reference like I showed you or a non-const reference. So what else is different about these things? Well, because you have to assign it once and only once when it is defined, or that also is true of this, right? What does that mean? I define it here, but I didn't give it an initial value. I didn't assign it a value up here. Well, remember that the context of this function is created every time it's called. When the activation record is created, one could argue that is when this is assigned the reference to, in this case, num. So that rule still holds. Once and only once can you ever assign a reference to the thing that it aliases, okay, the thing it refers to. And every time you call a function, that's what you're doing by picking which variable you're going to pass as an argument to that function by reference, okay? After you do that, it's completely immutable, right? How do you change the value of the reference? I can't say numref equals, x over here. I can't say int x and say numref is now x. If I do this, what I'm doing, if x is 22, what I'm doing here is assigning to this number variable down here. Okay, I'm replacing the value plus 10 with just simply 22. And I can't say things like ampersand numref down here or star numref equals this. No, none of that works. So what I'm getting at here is numref is truly immutable, can never be changed once it is either constructed in the activation record or constructed down here when it's initially defined. So what else do we know about references? Well, you cannot assign them null. I can't say something. Well, let's go ahead and try it and see what the compiler says. Ampersand rnum equals null ptr, right? What does that even mean? Null pointer is not an int, therefore this won't even compile because it's the wrong data type, right? Because I don't know what the heck am I doing here. Oops. I'm even worse because I use the same variable name. Let's call this, XXX because it's going to break anyway. All right, so what does it say? Invalid initialization of a non-const reference to a type int reference from an R value of this thing, which gets us to R values. We'll talk about that in another discussion, okay? The short of it is R value and L value are words that refer to in the most general terms. There's some specifics, but in general, the thing on the left side of an equal sign is usually referred to as an L value, and the thing on the right side of an equal sign is called the R value. So what it's really saying is the thing on the right of the equal sign is not compatible with the thing on the left, all right? You can't do that, in other words. So to wrap things up, why then do we have both pointers and references? Since, I mean, in theory, it could do the same thing either way, all right? It gets back to this operator overloading stuff. When we get to operator overloading, it's going to be difficult, impossible, quite frankly, to overload your operators without using references. So you're going to have to deal with that. Now, you might also ask, why use pointers if references look like they're easier to use, right? Because, well, I declare this reference to numref up here, and then I just use it like any old integer. This seems much easier to deal with than remember to put the star in front when you want to assign the value of the thing that numref would point at otherwise if it was a pointer, versus changing the value of the pointer itself, right? Well, it turns out that in order to deal with dynamic memory management, and that's the subject of a whole nother set of tutorials as well, but when the time comes and we deal with things that are dynamically created and deleted, we're going to have to use pointers. You can't use reference for those. The word dynamic should be a clue there. You cannot reassign a reference once it's been created. To manage things that are dynamic in nature, you need to be able to change them after the fact. And we'll see this crop up when it comes to creating things that are called linked lists and other data structures that have pointers inside of them that point to other things. You can't do it in any other way. The other thing that's different is, as we saw with arrays, if I ever create a function down here, that takes an array, maybe 20 elements or something like that, because this comes from C, right? This is part of the C++ that got inherited from C. Array is a pointer. A is passed by address here. In order to be compatible with its predecessor language, you have to be able to deal with this situation. You have to have pointers, period. Now, again, the argument could be you don't need to have references, and you could have done the language. The designers could have done the language without the references, but it would have made things more complicated in some other areas. So you got this, double-edged sword. And if you actually survey other computing languages that deal with references, you have the notion of when you want to modify the reference or the pointer versus when you want to modify the thing that the reference refers to or the pointer points at. So you have to pick one of two evils. Do you complicate the grammar of the language to deal with pointers in two different ways when they're acting differently? Or do you just have two different constructs? One of them is a reference and one is a pointer. And it was just a simple choice. The designer of the language chose to have two different constructs, two different types of things. All right, you have a pointer, which is an address of a thing that's dynamic, and you have an alias, which is a reference that is not dynamic. It's as simple as that. Thanks for watching. See you next time.